Hello, my name is Michael Sinclair, and today I'm going to be presenting on software-defined networking. I'll be going over what SDN is and its benefits, which include its high levels of flexibility, adaptability, visibility, and streamlined management and provisioning over a network. I'll also be going over the different types of SDN, including OpenSDN, API-based SDN, the overlay model, and hybrid SDN. Finally, I'll be covering security concerns related to having a centralized controller, which leads to a single point of failure. I'll also be addressing performance-related concerns regarding latency and controller response time and throughput. So let's get into it. Software-defined networking is not just a technological evolution, it's a revolution in network management. SDN employs software-based controllers and APIs to redefine how we control network traffic and create virtual environments. Some of the key components are software controllers and APIs. The objective of this presentation is going to be to explore advantages, disadvantages, security concerns, and the significance of SDN. So what exactly is SDN? It's a transformation in networking. Unlike traditional methods, SDN uses software controllers to manage network traffic, giving us flexibility and simplifying administration. The core components include a centralized controller, automation, and southbound and northbound APIs for communication. Now let's talk about SDN applications. These are crucial as they utilize the SDN controller to relay actions and request resources. They provide services like network management, analytics, and security, essentially creating an environment where software dictates hardware behavior, making SDN more adaptable and responsive. Taking a look at the architecture on this slide, we can see the high-level overview of SDN. Notice how the control and data planes are decoupled, treating application servers as a dynamic resource pool for the virtual network. Network virtualization is a key player in SDN. It decouples network services from underlying hardware, essentially creating an entire virtual network. This abstracts physical components into software, improving flexibility and simplifying management. Now let's talk about SDN protocols. SDN utilizes programmable open source networking protocols like OpenFlow to manage and monitor data and network traffic. Northbound interfaces communicate between the controller and applications, while southbound interfaces facilitate communication between the controller and physical network hardware. An interesting aspect of SDN is the separation between the control plane and the data plane. The control plane makes decisions about data routing, while the data plane essentially moves the data packets. This separation provides greater flexibility and supports dynamic routing. So what is the purpose of SDN? Well, it supports various functions like DevOps, application updates, and IT infrastructure improvements. It enhances complex networks, including campus networks, by providing higher automation and centralized management. Plus, it can create distributed firewall systems for enhanced security. Now let's talk about the four main types of SDN: OpenSDN, API-based SDN, the overlay model, and hybrid SDN. OpenSDN relies on protocols like OpenFlow, providing centralized control over network devices, while API-based SDN uses programming interfaces for monitoring and controlling network traffic. The overlay model involves a virtual network layered on top of existing hardware. Channels facilitate data movement between data centers, keeping the physical network itself unchanged. The hypervisor acts as an interface between physical devices and the virtual network, while hybrid SDN is a combination of SDN and traditional networking. It optimally assigns protocols for different types of traffic, allowing gradual adoption into legacy environments. It supports various network topologies, but demands advanced management skills. Now let's take a closer look at an example of SDN in action. On this slide, we have an OSPF network split into different parts connected by SDN nodes. Traditional routers typically update their routing tables during network changes. However, in an SDN environment, the game changes. SDN nodes play a pivotal role in relaying this information to the central controller. As the network evolves, the SDN controller optimizes routing settings, emphasizing load balancing. These optimized settings are then applied through SDN nodes at the edges of each network part. This ensures an efficient and balanced flow of data throughout the network. It's a prime example of how SDN brings a new level of adaptability to network management, optimizing routing configurations for improved performance and dynamic management. While SDN and traditional networking share similarities, SDN has the advantage of centralized intelligence. It simplifies security policy management and scalability without relying on expensive hardware. Now, speaking of security, SDN introduces a shift in security dynamics. It allows for adaptable and dynamic security measures, scaling effortlessly with evolving network requirements. This approach ensures consistent zero-trust access across the network, significantly enhancing overall network security. Now let's explore the benefits of SDN. It provides comprehensive visibility, lower operating expenses, and improved resource utilization, resulting in a higher return on investment and reduced total cost of ownership over the network's lifecycle. Businesses can leverage SDN to create a central cloud, consolidating all infrastructure components. This simplifies network management, enhances overall operational efficiency, and facilitates the seamless movement of data between distributed locations. SDN contributes to telecommunications optimizations through network functions virtualization. It enables the shift of customer services to less costly servers, making networks highly adaptable to changing demands. The speed and flexibility of SDN makes it ideal for supporting emerging technologies like edge computing and the Internet of Things. These technologies require rapid and efficient data transfer, a capability that SDN inherently provides. Taking a look at SD-WAN, it's a smart and automated wide area network. SD-WAN dynamically directs and secures traffic based on application rules, network conditions, or the priority of the wide area network circuit. While SDN enhances security policy management, it introduces a potential single point of failure, the controller. Implementing redundancy measures and protecting against DDoS attacks are crucial steps to ensure business continuity and security. Now let's talk about performance. The separation of the control and data planes can introduce latency, influencing network performance and scalability. Balancing intelligence in the data plane is essential for improved performance without sacrificing virtualization. In conclusion, SDN represents a significant advancement in network management. By leveraging software-based controllers and APIs, SDN revolutionizes how we manage network traffic. It offers a range of benefits, but comes with a set of security challenges and potential latency issues, requiring careful implementation and management. That'll wrap up our presentation on software-defined networking. Thank you for watching.